Chaos theory is a branch of mathematics and physics that studies the behavior of complex and dynamic systems that are highly sensitive to initial conditions. It explores the inherent order and patterns within seemingly chaotic and unpredictable systems. The butterfly effect, an underlying principle of chaos, describes how a small change in one state of a deterministic nonlinear system can result in large differences at a later state, meaning there's a sensitive dependence on initial conditions. A metaphor for this behavior is that a butterfly flapping its wings in Texas can cause a tornado in Brazil. Small differences in initial conditions, such as those due to errors in measurements or due to rounding errors in numerical computation, can yield wildly diverging outcomes for such dynamical systems, rendering long-term prediction of their behavior impossible in general. This can happen even though these systems are deterministic, meaning their future behavior follows a unique evolution and is fully determined by their initial conditions, with no random elements involved. In other words, the deterministic nature of these systems does not make them predictable. This behavior is known as deterministic chaos, or simply chaos. The amount of time for which the behavior of a chaotic system can be effectively predicted depends on three things: how much uncertainty can be tolerated in the forecast, how accurately its current state can be measured, and a timescale depending on the dynamics of the system. Key concepts of chaos theory. Key concepts of chaos theory include nonlinear dynamics. Chaos theory primarily deals with nonlinear dynamical systems where the relationship between variables is not proportional. Nonlinearity often leads to complex and unpredictable behavior. Sensitive dependence on initial conditions. A hallmark of chaotic systems is their extreme sensitivity to initial conditions. Small variations in the starting conditions can lead to vastly different outcomes over time. This phenomenon is popularly known as the butterfly effect. Deterministic chaos. Despite the appearance of randomness, chaotic systems are deterministic, meaning their future states are entirely determined by their initial conditions and fixed rules. The apparent unpredictability arises from the sensitivity to initial conditions. Fractals. Chaos theory is closely associated with the study of fractals, which are complex geometric shapes exhibiting self-similarity at different scales. Fractals are used to describe the intricate patterns found in chaotic systems. Bifurcations. As parameters in a chaotic system are varied, the system may undergo bifurcations, resulting in a progression of complex behavior, including periodic, quasi-periodic, and chaotic states. Applications. Chaos theory has applications in various scientific fields, including physics, meteorology, biology, economics, and computer science. It's been used to model and understand phenomena such as weather patterns, fluid dynamics, population dynamics, and the behavior of financial markets. The study of chaos has provided valuable insights into the nature of unpredictability and complexity in natural and artificial systems. Critics of chaos theory often raise concerns about its applicability, methodological challenges, and the broader implications of understanding complex systems. One major criticism revolves around the difficulty in predicting long-term behavior in chaotic systems, which is a fundamental characteristic of chaos theory. Detractors argue that the sensitivity to initial conditions and the resulting unpredictability may limit its practical use in certain fields, particularly where precise predictions are essential. Another criticism is related to the definition and identification of chaotic behavior. While chaos theory provides a framework for understanding systems exhibiting sensitivity to initial conditions, some critics contend that the criteria for defining chaos can be subjective or lack clear boundaries. This raises questions about the reliability and consistency of identifying chaos in real-world systems. Additionally, the reliance on mathematical models and simulations in chaos theory has faced skepticism. Critics argue that the choice of mathematical models and the accuracy of simulations can significantly influence the results. They emphasize the challenge of accurately representing complex real-world systems and suggest that the limitations of available data and modeling techniques may impact the validity of the conclusion drawn from chaos theory. There's also a broader philosophical criticism related to the deterministic nature of chaos theory. Some critics argue that emphasizing determinism in chaotic systems may oversimplify the inherent probabilistic and indeterministic aspects of certain phenomena. This perspective emphasizes the limitations of a purely deterministic approach and calls for a more nuanced understanding of randomness and probability in complex systems. Despite these criticisms, it's important to note that chaos theory has made significant contributions to various scientific fields and has provided valuable insights into the behavior of complex systems. Many researchers and practitioners acknowledge its limitations while recognizing its potential to enhance our understanding understanding of dynamic and unpredictable phenomena. Ongoing research and interdisciplinary collaboration continue to refine and expand the applicability of chaos theory. If you like this kind of philosophical subject matter, help us grow the channel by liking the video and subscribing to the channel.